Hello guys, I'm Anantha. In this video, me and my friend will run you through a simulation illustrating the effect of peak cell rate and cell delay variation tolerance on the performance of an ATM network. Before moving on to the simulation, let's touch upon some basics of ATM networks. ATM stands for Asynchronous Transfer Mode. An ATM network is a connection-oriented packet switching technique, which means it requires a connection setup prior to the transfer of the packets. It provides quality of service guarantees on a per connection basis. Generally, ATM switches come in a variety of types and sizes. A small switch is called Customer Premise Equipment or CP. A large switch is called a Central Office Switch. The ATM interfaces can be classified as network to network interface, which is the interface between ATM switches, or user to network interface, which is the interface between an ATM switch and an end user. Here is an example of a network where the source user interacts with the network through a UNI. The connection request must propagate across the network and eventually interact with the destination UNI. Within the network, the switches must interact across the NNI to exchange information. ATM combines several desirable features of packet switching and time division multiplexing circuit switching. Hence, an ATM network can handle variable bit rates, variable delay, and bursty traffic. ATM involves a conversion of all information flows into 53-byte fixed length packets called cells. Cells contain 5-bit headers, which are essentially pointers to the tables in the switches. Now, let's look into the concepts of virtual channels and paths. ATM uses a connection-oriented paradigm in which an application first creates a virtual channel, uses the channel for communication, and then terminates it. Virtual paths achieve bundling of virtual channels in a transmission path. Here is an example of a transmission path containing various virtual paths and the corresponding virtual channels. This figure shows the format of an ATM cell, which includes the header and the payload or the information. The header of the ATM cell allots 4 bits to the GFC, which was intended to provide flow control. However, it is currently undefined and is set to 0. 16 bits are allotted to virtual circuit identifier, 8 bits are allotted to virtual path identifier, and a 3-bit payload type identifier allows 8 types of payloads. 1 bit is allotted to cell loss priority, where cells with CLP is equal to 0 are given higher priority over the cells with CLP is equal to 1. The header error check is a 8-bit CRC checksum which can correct all single errors and detect all the double errors. The following 3 quality of service parameters may be negotiated between the user and the network during a connection setup. The cell loss ratio for a connection is the ratio of the number of lost cells to the total number of transmitted cells. The cell transfer delay is the time that elapses from the instant when a cell enters the network at the source UNI to the instant when it exits at the destination UNI. Cell delay variation measures the variability of the total delay encountered by the cells in a connection. When creating a virtual channel, a user must specify the following traffic descriptors. Peak cell rate specifies the rate in cells per second that the source is never allowed to exceed. Sustainable cell rate is the average cell rate in cells per second produced by the source over a long time interval. Maximum burst rate specifies the maximum number of consecutive cells that the source can transmit at the peak cell rate. The minimum cell rate is the minimum average cell rate that the source is allowed to send. The cell delay variation tolerance specifies the level of cell delay variation that must be tolerated in a given connection. Having learned some basic concepts on ATM networks, let's move on to the simulation.
Hello everyone, I'm Shirin Fathima, and in this video I would like to explain the creation of a simple ATM network and its simulation in NetSim software. The main objective is to study the effect of peak cell rate and cell delay variation tolerance on the performance of an ATM network. First of all, we choose the environment that we want to work with. Here we choose legacy networks and then choose ATM, that is asynchronous transfer mode. In this environment, we will create an ATM network model. A network model is nothing but a flexible way of representing devices and their relationships. First, we choose a CPE, that is Customer Premises Equipment. We place two CPEs in our network, CPE1 and CPE2. Customer Premises Equipment is any terminal and associated equipment located at a subscriber's premises. It generally refers to devices such as telephones, routers, set-top boxes, etc. that enable consumers to access communication service providers' services and distribute them around their house via a local area network. Next, we would be placing two ATM switches between the two CPEs. We select ATM switch and place them between CPE1 and CPE2. ATM is a synchronous transfer mode. It is a connection-oriented technology that requires the establishment of a specific network path between the 2 points before any data can be transported. Hence, we select a wired link and connect the 4 devices. Link 1, Link 2 and Link 3. Next, let us see the parameters that we need to change for CPE1 and CPE2. The first parameter is transmission type, that is point to point. Data transfer between two designated stations, CPE1 and CPE2. Destination is CPE2. Traffic type is data, that is, we want to transfer data between the two CPEs. Application data size is kept as default 1500 and the distribution is made exponential. Inter-arrival time, that is, the time delay between successive packets. Smaller inter-arrival time leads to more packets being generated per unit time and vice versa. The distribution is kept as exponential. Next is the generation rate. The rate at which traffic is generated by the node is called the generation rate. A simulation run is stable if the total generation rate is lower than the rate at which this can be serviced by the links. Therefore, the generation rate is equal to application data size by mean arrival time, hence 0.6. The next is MTU, that is maximum transmission unit. The largest frame size that can be transmitted over the network is called MTU. Messages longer than the MTU must be divided into smaller frames. Scheduling is the process of determining the order in which packets in a queue should be processed. Packets may reach a switch from different directions. Round-robin scheduling lets every packet from different direction to take turns in transferring packets in a aperiodic manner. Next, let us change the peak cell rate. This specifies the rate in cells per second that a source is never allowed to exceed. We'll keep it as 1000. Cell delay variation tolerance is also kept as 1000, which is the maximum allowable cell delay variation between two end stations. We change the parameters of CPE2 as well similarly, but here as you can see the destination is CPE1. Traffic type is again data and we change the parameters as we did in CPE1. Next, let us look at the parameters for the switch. It has scheduling technique, that is again the order in which packets in a queue must be processed. In a complex network, packets may reach a router from many directions. Priority scheduling algorithm will allow the router to fix priority level for different sources from different directions. Higher priority packets are processed first and sent out. Next is the buffer size. Buffer is the memory in a device which holds data packets temporarily. If the transmitting port is busy, incoming packets are stored in the buffer. As you saw, the range was from 1 to 5 megabytes. We changed the properties of switch 2 similarly. Next, let us look at the link properties. First is the bit error rate. By default, it's 10 power minus 6, but we'll take an ideal case for no error. Physical medium is E0. These are just standards in which it has a fixed size, rate and degree of attenuation. The data rate is 0.064 and the distance of the links is kept as 1 kilometer. Now our network model is ready, hence we can run simulation. Simulation time is kept as 10 seconds. If needed, we can increase it. As the simulation is over, we would be able to see the network performance. Here, as you can see, there are many performance metrics for the given network. There is user level throughput, you have simulation time, we have the payload delivered and many other metrics. The fundamental parameters that measure the performance of a network are utilization and delay. We can see these values as a pie chart. We can also see these values later in NetSim analytics. First, we save the sample. Let's name it experiment 1. Next, we go to the NetSim analytics. Here, we'll choose legacy networks and see the sample that we just saved, experiment 1. In the graph, we need to see queuing delay for our experiment. As you can see, many parameters are available in form of a table: utilization, overhead percentage, loss percentage, delay, queuing delay, medium access and transmission time. Utilization is the fraction of available bandwidth used for transmission of data and it is expressed as a percentage. Delay is the amount taken for a packet to travel from one end of the network to another. Delay is basically the sum of queuing delay, transmission time and medium access time. Queuing delay is the time the packet or frame waits in a queue prior to transmission. When packets arrive at a router, they have to be processed and transmitted. Only one packet can be processed at a time. If packets arrive faster than the rate at which they are processed, packets are put into a queue, also called a buffer. The maximum queuing delay is proportional to the buffer size. If arrival rate exceeds the transmission rate, either the packets will be queued and wait to be transmitted, or if the memory buffer fills up, the packets may be dropped or lost. Transmission time is the time taken by a packet to travel across one hop and the other. Medium access time is the time the data waits in the head of the queue to access the medium. The loss percentage is 0 here. As you remember, we kept the bit error probability as 0. Next, we change the peak cell rate and cell delay variation tolerance values to 2000. We click on Modify to change these values and make it 2000. All other parameters are kept as it is. Need to change for CPE2 as well. Now we run the simulation. Simulation time is again kept as 10 seconds. Now we save the experiment. Say we give name experiment 2. The sample has been saved. Now we go to NetSim Analytics. Again we go to Legacy Networks, select the metrics as queuing delay, and let me put experiment 1 as well as experiment 2 so that we can compare both samples. As you can see, utilization, loss percentage, delay, everything is available. Next, we choose peak cell rate and cell delay variation tolerance as 3000, 4000 and 5000 respectively for experiment 3, 4 and 5. Now we have 5 samples. As you can see, the utilization percentage has saturated to around 99%. Next, the queuing delay, which we mainly wanted to look at. The queuing delay has increased as we increase the peak cell rate and cell delay variation tolerance from 1000 to 5000. As we change these values, the number of cells transmitted also increases. As we know, peak cell rate is the maximum number of cells that can be transmitted per second. Therefore, as we increase the peak cell rate, number of cells transmitted per unit time also increases. As the number of cells transmitted per second increases, queuing delay also increases as more cells start queuing up. All the other parameters like buffer size, net data size, etc. remain the same in all cases. Thank you. Hope the video was helpful.